Welcome to the lectures in chemistry and on the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology as a professor of chemistry. The email IDs are given below for you to write to me or for any other contact related to the course materials. This lecture is a follow up on the last lecture on the infinite series representation and infinite series solution, what is known as the power series solution for the differential equations. As the first serious example, we shall look at the Hermite's differential equation, which is the basis for solving the harmonic oscillator problem and also getting the exact eigenfunctions. So, please remember the two most important aspects of the last lecture on power series are: one, a proposal for the wave function solution in terms of, say in the case of one dimension as an x coordinate, a solution in terms of an infinite series indexed by the integer n in x raised to n. And then the second is a recurrence relation which determines coefficients a n in terms of other coefficients, in terms of a naught, a 1, etc., a 2, etc. Okay. So, these two things will be again the important aspects of today's this lecture on the Hermite's differential equation. First, let us recall the harmonic oscillator Hamiltonian. For an oscillator with a mass mu and a force constant k, the Hamiltonian is minus h bar square by 2 mu d square by dx square plus half kx square, okay, kinetic energy and the potential energy. Therefore, the solution that we are looking for is the h psi of x is equal to E psi of x. This is the differential equation and the solutions are psi and E. Therefore, if we rewrite the differential equation, we will have d square psi by dx square plus 2 mu E by h bar square minus k mu by h bar square x square psi of x is equal to 0, psi of x is equal to 0. Now, let us introduce the constants. Let us introduce lambda as 2 mu E by h bar square and another constant alpha square as k mu by h bar square. Then the differential equation is d square psi by dx square plus lambda minus alpha square x square psi of x is equal to 0. Okay. Now, the idea of writing different constants and also the equation in a different way is to remove the dimensional dependence and write a reduced equation using variables which do not have dimensions. Here, please remember x has the dimension of the displacement, that is the length of the oscillator from the equilibrium, displacement from equilibrium. Therefore, there is a physical aspect of the harmonic oscillator which is part of the mathematics, and then you have the Planck's constant h bar, you have the energy which is also a dimension to quantity, the mass of the oscillator all these things are there which are specific to the oscillator itself. Let us remove the oscillator specific details and will write an equation which will be applicable to all oscillators independent of what the mass is and so on. This is done in physics usually using dimensionless variables instead of the dimensional equation. So, let us introduce a dimensionless variable y is equal to root alpha x and see why it is a dimensionless variable. If you recall the definition of alpha, it is alpha square is k mu by h bar square. Okay. Alpha square k mu by h bar square. K is the force constant. The dimension of k is mass per square, inverse mass times inverse square of time, and the reduced mass mu is also mass, and h bar square, leaving the angles out, it is basically mass length square t minus 1 whole square, because it is a square of the Planck's constant. So, the definition of alpha square is such that the dimension of alpha square is 1 by L square, 1 by L to the 4, okay, because the other things cancel off. Therefore, root alpha times x, if you define that as y, x having the dimension of length and square root of alpha being 1 by length, y is dimensionless variable. Okay. Therefore, to do that, let us go back and write the differential equation again. D square psi by dx square times 1 by alpha plus lambda by alpha minus alpha x square psi of x is equal to 0, and then introduce now y is equal to root alpha times x. Therefore, d by dy will be 1 by root alpha d by dx. Okay. D by dy is d by dx and dx by dy, and you know x, therefore, this is that. Okay. So, the equation now becomes the function psi is a function of x. Now, we replace x by y, it is a different function. So, let us call this as psi of y. Therefore, the differential equation, this one becomes d squared psi by dy square plus lambda by alpha minus y square psi of y is equal to 0. So, this is the differential equation in which the parameters related to the harmonic oscillators have all been removed. There is of course lambda by alpha, but we will find that out soon, how to handle it. Okay. But the variable y is a dimensionless variable. So, this differential equation, namely this is valid for all values of y, namely from minus infinity to plus infinity. So, in dealing with differential equations of this kind, which take the entire range of real values, the first is to look at the asymptotic solutions. Asymptotic solutions refer to x going to plus or minus infinity, large values. Okay. For very large, here of course is y that goes to plus minus infinity. Okay. Therefore, for very large values of y, it is possible to ignore this contribution, which is a constant, and write the differential equation as d square psi by dy squared minus y squared psi is approximately 0, okay, because lambda by alpha is much less than y squared, large y. Then for this equation, an obvious solution, an obvious I would say approximate solution is e to the plus or minus beta y squared. if we consider this psi to be approximately of this form e to the plus or minus beta y square, then you can immediately write d square psi by dy square is plus or minus 2 beta. It is a simple derivative. So, let me write the result e to the plus or minus beta y square plus 4 beta squared y squared e to the plus or minus beta y square. Okay. That is this term, and minus y square psi. So, if you want to write to the differential equation with this and that. Okay. You will see that the equation that we have to write is d square psi by dy square minus y squared psi is equal to 0 goes over to the condition that y square into 4 beta squared minus 1 plus or minus 2 beta times e to the plus minus beta y square is equal to 0. Okay. This never goes to 0 except at infinity. Therefore, the solution that you have to look at is y is equal to 2 beta, or y square is equal to 2 beta by 2 beta plus 1 2 beta minus 1. This is also this is y square, so it is minus plus, and the for y going to infinity, obviously 2 beta is equal to 1, and you can see that the solution beta is plus minus half. Okay. It is y going to minus infinity, of course it is 2 beta is equal to minus 1. Okay. Therefore, either way you have this, but the exponential function e to the plus half beta square, half y square goes to infinity. Therefore, it is not a wave function that we need or we would consider, cannot be normalized. Therefore, let us take the solution psi of y for large values of y e to the minus half y square, large y, absolute value of y. Okay. Because plus minus y, it does not matter, the function has the same value. What is the exact solution that we are looking for? Therefore, psi of y is some function of y multiplied by e to the minus half y square, such that for very large values of y, this function behaves like e to the minus half y square. Okay. So, we need to introduce this function h, and this h will turn out to be a polynomial, as we will see soon. Okay. So, let us use this definition, namely psi of y as h of y times e to the minus half y square, and now consider the full differential equation d square psi by dy square plus lambda by alpha minus 1 minus y square psi is equal to 0. Okay. If you take the derivatives, you can see immediately this result, namely e to the minus half y square times the second derivative of the function h minus 2y dh by dy plus lambda by alpha minus 1 h. This would be 0. This is substituting this function in this equation. the differential equation that you get is the following. And since this is valid for all values of y and this does not go to 0, the differential equation known as Hermite's differential equation is this form: 1 d square h by dy square minus 2y dh by dy plus lambda by alpha minus 1 h is equal to 0. Therefore, our objective is to find out h, to determine h. Now, for doing that, let us propose h of y is a power series, namely sum over n equal to 0 to infinity some constant a n times x raised to n. So, at this point now you see that this is a starting point from the previous lecture on the power series. Therefore, this is the differential equation that we have to solve, and this solution h, if you recall, is part of this solution, namely the full solution. The wave function is h of y multiplied by the Gaussian function e to the minus half y square. Therefore, the chain should be clear. One should be able to follow the trails quite carefully. Okay. So, let us look at h of y given by this definition and then substitute the derivatives and the second derivatives and so on. So, this is n equal to 0 to infinity a n x y raised to n. I am sorry, it is not x, it is y. Y raised to n, and I think in the previous is also, this is also y raised to n. Okay. Okay. Oh. dh by dy is the sum n equal to 1 to infinity n a n y n minus 1, and d square h by dy square is the second derivative, namely n equal to 2 to infinity n into n minus 1 a n y n minus 2. Okay. This we will substitute in the differential equation here, d square h minus 2y dh by dy, this one. So, when you do that, the substitution gives you the following. Two a2 plus 2 into 3 a3 y plus 3 times 4, 3 into 4 a4 y square plus etc. plus n plus 1 into n plus 2 a n plus 2 y raised to n plus etc. This is the first term, and this term is essentially this one. D square h by dy square. The next term is minus 2 dh by, if you recall, the next term is minus 2y dh by dy. Therefore, dh by dy, every term is multiplied by y to give you a1y plus 2 a2 y squared plus 3 a3 y cube plus n a n y raised to n. Okay. And the last term is of course the h itself multiplied by lambda by alpha minus 1. Therefore, the last term is lambda by alpha minus 1 times h, which is a naught plus a1 y plus a2 y squared plus a n y raised to n plus so on is equal to 0. As usual, we will see that every term is either a constant or a power of y. So, we will equate each coefficient of y to the power n, n equal to 0, 1, 2, 3, etc. each one we will set it to 0 in order to obtain the solutions in the final form. Therefore, the first term, if you look at the coefficient of y raised to 0, that is the constant term, if you look at, you can see immediately that the terms are 2a2, there is no power of y here, and then there is also lambda by alpha minus 1 times 0. Okay. So, these are the only two terms without any y. Therefore, the first term is 2a2 plus lambda by alpha minus 1 a0 is 0, and the coefficient of y to power 1, you can see it immediately here, 2 times 3 a3y minus 2 times 2 a1y, and then there is a1y. So, again you can see this relation, namely a3 and a1 are connected, a2 and a0 are connected, and you can see this kind of odd even relationships in most of these equations. Coefficient of y1, y raised to 1, namely coefficient of y itself, is 3 times 2 a3 plus lambda by alpha minus 1 minus 2 times 1 a1 is equal to 0. So, let me write a couple of more coefficients here. Coefficient of y square is 4 times 3 a4 plus lambda by alpha minus 1 minus 2 times 2 a2 is 0, and likewise for the coefficient of y raised to n, the general term is n plus 2 into n plus 1 a n plus 2 plus lambda by alpha minus 1 minus 2 times n a n is equal to 0. N plus 2 and n connected, which means odd series and even series that you will have. Okay. Therefore, the coefficient a2 is minus lambda by alpha minus 1 a0 by 2, and the coefficient a4 is minus lambda by alpha minus 1 minus 2 times 2 a2 by 3 times 4, which is given as minus 1 whole square. If you substitute for a2 from the above, you get lambda by alpha minus 1 minus 2 times 2 times lambda by alpha minus 1 a0 divided by 4 factorial. Okay. The general term is a to n is equal to minus 1 raised to n half. You see a4 is minus 1 square, a2 is minus here. Okay. a2 is minus 1 raised to n lambda by alpha minus 1 minus 2 times 2n minus 2 lambda by alpha minus 1 minus 2 times 2n minus 4 all the way down to the last one when n is 0, n is 2, you will see that lambda by alpha minus 1 times a0 divided by 2n factorial. Okay. This is the recurrence relation between all the even coefficients a0, a2, a4, etc., all of them. And of course, the odd coefficient, if you follow the same mathematics, it is immediate to write this down. So, the coefficient a to the 2n plus 1 is related to the coefficient a1 by the formula exactly the same way as above, minus 1 is to n 2n plus 1 factorial times lambda by alpha minus 1 minus 2 times 2n minus 1 lambda by alpha minus 1 minus 2 times 2n minus 3 all the way to lambda by alpha minus 1 minus 2 into 1 times a1. Therefore, you have the relationship of A1 to A3, A5, A7, etc., and the relationship of A0 to A2, A4, A6, etc. So, therefore, we know the h of y as an infinite series. The difficulty is that h of y is multiplying e to the minus y square by 2. It is important that h of y does not increase faster than e to the minus y squared decreasing, or at least the same as the rate of increase of h of y term by term. If you look at it, it should be faster, it should not be even the same as that of this one, because then the series will not converge, the product will not converge to give you a finite wave function. The square of the wave function should go to a finite value when you integrate. Remember, ultimately we have to have this property psi of x dx from minus infinity to plus infinity. This should be normalized to 1. If this tends to infinity, then this function is not very good. Take a quick look. A n plus 2, if you take the ratio to a n, then you will see that the term is minus lambda by alpha minus 1 minus 2 n divided by n plus 1 into n plus 2. So, this is of the order, when n is very, very large, this lambda by alpha minus 1 is irrelevant. This is of the order 2n by n square, and the other terms can also go to, they can be removed because n is very large, n square is the leading term. So, it is 2 by n. The unfortunate thing is exponential minus y square also decreases in the same order 2 by n. Okay. So, we have a problem if we take these two together, that this function will not, the Hermite polynomial, Hermite function, the infinite series is not the right solution, but the Hermite function should be, series should be truncated. To finite terms. Only then the product function will be acceptable as a wave function for the harmonic oscillator problem. So, if you have to truncate this function, then Hermite series should be a polynomial. What it means is that for some n, a n may not be 0, but all the other terms a n plus 1, a n plus 2, all these coefficients should be 0. Then the series is truncated to a finite value, then you can write h of y as n equal to 0 to some finite n, e n y raised to n. This will be the requirement in order for the wave function to be normalizable. So, if you have to make this to a finite value, let us write the h of y based on the a n's we have written down so far. The even terms are all a n 1 minus 2 n by 2 y squared plus 2 n minus times 2 n minus 4 by 4 factorial y raised to 4 and so on. Okay. So, what we have assumed is that lambda by alpha minus 1 minus 2 n is 0 for some n, and therefore, lambda by alpha minus 1 is equal to 2 n. That is put in here. Okay. Then you have, let me write the next term for the series, minus 2 n times 2 n minus 4 times 2 n minus 8 divided by 6 factorial y raised to 6 plus etc. This is the even number of terms, and the odd coefficients are all connected to A1. They will be y minus 2n minus 2 by 3 factorial y cube plus 2n minus 2 times 2n minus 6 by 5 factorial y raised to 5 minus one more term. I will write 2n minus 2, 2n minus 6, 2n minus 10 divided by 6 factorial y raised to 7 plus etc. Okay. But it is truncated to the value n. What is the value of n? N can be 0, n can be 1, n can be 2. Each n gives you one Hermite polynomial. So, the truncation is important in the sense that the physical parameters lambda by alpha. So, let me highlight these. The physical parameters are there in lambda and alpha. Remember, lambda was given in terms of, if you go back to the lecture very early on, you can see what was the definition of lambda. From the differential equation, we had put in lambda is equal to 2 mu e by h bar square. So, here is the physical constant, and alpha is k mu by h bar square. Okay. So, lambda and alpha determine the physical parameters, and the physical parameters are chosen such that this condition is approximately valid, lambda by alpha minus 1 is 2n. Then the Hermite polynomial is truncated to the last term, okay, only to that term. And the convention is to choose for Hermite polynomials the constants a0 and a1 are chosen so that the maximum term, so that the last y raised to n term, okay, has the coefficient as follows. For even n, a0 is chosen as minus 1 raised to n by 2 n factorial by n by 2 factorial, and for odd n, it is possible for us to write this. This is a convention in the choice of the Hermite's solution. A1 is written as minus 1 to n minus 1 by 2 times 2 n factorial divided by n minus 1 by 2 factorial. Okay. This is the highest term, that is the y raised to nth term. Therefore, with this convention, now we can write to the Hermite polynomial as follows. The first Hermite polynomial, namely when n equal to 0, the h 0 of y will become 1. Okay. It is just a0, okay, which you can see right away, that if n is 0, all of this gets to 1. 0 factorial is 1. Okay. If you choose n equal to 1, the h1 of y will give you the value 2y, which is also easy to see. You are only retaining the first term, you are not keeping, because now n is limited only to 1. Therefore, when n is 2, this term goes to 0, all the other terms go to 0. So, when n is 1, you have the odd n here, minus 1 raised to n minus 1, 2 n factorial is 1, and then you have n minus 1 by 2 factorial, that is also 1. So, you have 2, therefore, the coefficient a1 is 2, and therefore, the expression is 2y. Okay. So, likewise, n equal to 2, h2 of y becomes 4y square minus 2, n equal to 3, h3 of y becomes 8y cube minus 12y. You see that this means a0, this also means a0 and a2, and let me write one more term, n equal to 4, h4 of y is equal to 12 minus 48y square plus 16y raised to 4. This means only these 3 coefficients a0, a2 and a4 are chosen, and n has that value, and n equal to 5 is the last term I will write, h5 of y, which is 120y minus 160y cube plus 32y5, and all these numbers come from the choice of those things. Therefore, this you can see now, this is a1, this is the choice of a1 and a3, this is the choice of a1, a3 and a5. So, the Hermite polynomials are such that you see that there is an even polynomial, there is an odd polynomial depending on which constant you choose, and these coefficients are connected by the recurrence relations that we had earlier. This is the recurrence relation that we had, and in this therefore, we have chosen the condition that lambda by alpha minus 1 is equal to 2n. So, when n is 0, of course, you get a0, when n is 1 you get a1 and so on. Therefore, what is the final solution now? The final solution psi of y is e to the minus y square by 2 h n of y, and since n is chosen as 0, 1, 2, 3 etc., subject to the condition lambda by alpha minus 1 is equal to 2n. Now, let us look at lambda. Remember, lambda is 2 mu e by h bar square, and alpha is equal to, alpha square was chosen as k mu by h bar square, and alpha therefore is basically square root of k mu by h bar square. Therefore, what is lambda by alpha? If you do that, it is 2 mu e by h bar square into h bar divided by square root of k mu. Okay. So, you have mu to the 1/2, this mu is gone, and what is left over? You have a h bar is gone, h bar square, you have a h bar down here. Therefore, lambda by alpha turns out to be 2 mu to the 1/2 e by k to the 1/2 and a h bar, and that is lambda by alpha, and that is equal to 2n plus 1. Okay. Therefore, what is E? E is equal to 2n plus 1 into h bar into square root of k by mu divided by 2. Okay. And square root of k by mu, you know, is the angular frequency for the harmonic oscillator. For the oscillator. Therefore, what you have is the energy E now, in terms of the n values that you have chosen, E is given as n plus a half h bar omega, which is the same as n plus a half h nu, since omega is equal to 2 pi nu and h bar is h by 2 pi. Therefore, they cancel out when you take the product of these two. So, you see that the energy expression for the harmonic oscillator is now given in terms of n plus a half, where the possible values of n are 0, 1, 2, 3 etc., and the wave function psi n corresponding to this E n plus a half or this n is obviously h n of y e to the minus y square by 2. So, this is the sum and substance of the harmonic oscillator problem that we have. The rest of it, of course, I have already discussed in the harmonic oscillator model, how to normalize these functions and how to visualize the wave function as well as the square of the wave function and so on. Therefore, now you can connect to this. Let me leave you with the last conversion, namely, remember y is equal to root alpha x. Therefore, the wave function that we are talking about, psi of x, is now in terms of the the variables that we have here, it is Hn of root alpha x and e to the minus alpha x square by 2. The only thing that is missing is the normalization constant n, such that psi of x integral dx. Psi star is, of course, these are all real functions, so we do not need to worry about the star. This is equal to 1. Therefore, you can calculate n of n, and the general expression for n of n when you do the mathematics is also available, and let me write that down. The general expression for n is 2 raised to n factorial times root pi by alpha the whole square root. Okay, that is the general factorial, and therefore you can see that the harmonic oscillator wave function, the harmonic oscillator energies are all obtained from the very simple differential equation, namely the Hermite's differential equation. Okay. So, this whole exercise is to actually take you through the mathematics as in as detailed a manner as possible without worrying too much about the mathematical properties of some of these terms. But remember where the series comes from. The series comes from the fact that the Hermite, the infinite series, is truncated to give a finite polynomial, and the truncation means you truncate at various powers of n and various values of n. Therefore, you get a whole series of polynomials. What is the maximum value of n? N can go up to infinity. All it means is that the harmonic oscillator will remain as a harmonic oscillator even for extremely large values of x. But that is a mathematical limit. Molecules do not, oscillators do not, they all become anharmonic even after a small amplitude. Therefore, these functions are important in understanding the one important part of the analytical solution to the quantum mechanical problem, namely the differential equation for the harmonic oscillator and the Schrodinger equation. We will see only one more such equation, namely the spherical harmonics, which is also very important for all the angular momentum problems, and therefore I will take you through the infinite series solutions for the Legendre and the associated Legendre polynomials in the next lecture. And with that, this part of mathematics is to give you a feel that things are not hands-on. I mean, they are not, you don't wave your hands, but you actually sit down and do the mathematics carefully. Okay? Thank you very much.